Hello everyone, welcome to ashatech.com. In our series of answer questions in mechanical engineering science, we have another question. Part A says, define the following as used in shear and torsion. Roman 1, modulus of rigidity. Roman 2, torsional rigidity. And part B of this question says, a hollow shaft of diameter ratio 3 out of 5 is required to transmit 600 kilowatts at 110 revolutions per minute. The maximum torque being transmitted being 20% greater than the mean. The shear stress is not to exceed 60 Newton per square millimeter, and the twist on a length of 3 meters not to exceed 1 degree. Calculate the minimum external diameter of this hollow shaft to satisfy the above conditions. Take G, which is the modulus of rigidity, as 80,000 Newton per square millimeter. Let's go ahead and answer this particular question. A Roman 1, we are defining modulus of rigidity as the ratio of shear stress to shear strain. Therefore, if modulus of rigidity is G, it is equal to shear stress tau divided by shear strain gamma, and it is given in Newton per square meter. Part 2 says we define torsional rigidity, and it has been defined as the ratio of torque to the angle of twist, which is in radians per unit length. Okay, so if we recall torsional theory, from torsional theory, T out of J, torque applied divided by J, which is the polar second moment of area, is equal to tau, which is the shear stress due to this torque, divided by R, which is the outer radius, is equal to G theta, whereby G is the modulus of rigidity, and the theta is the angle of twist, L is the length of that particular shaft or member that we are considering. So now, when we consider T out of J equal to G theta out of L, when we reorganize, we get something like GJ equaling to T out of theta out of L. So GJ is what we call the modulus of rigidity, which is equal to the ratio of torque to twist angle per length. We have answered that one. Let us go to part B. We have the ratio of diameters. This means the inner diameter to outer diameter is actually like this. Inner to outer is 3 to 5. That's what it means. Therefore, we also given that the power to be transmitted is 600 kilowatts. That is 600 times 10 to the power 3 watts, and the speed in revolutions per minute is 110. The angle of twist is 1 degree, and from the fact that 360 degrees are equivalent to 2 pi radians, it means to get 1 degree, it will be 2 pi divided by 360. We multiply by 1 for us to get the number of radians in 1 degree. So which is equal to 1 times 2 pi out of 360, giving us 0.0175 radians. Again, we are given that maximum shear stress tau is given as 60 Newton per square millimeter, and converting it to Newton per square meter, it gives us 60 times 10 to the power 6 Newton per square meter. What about the maximum torque? It has been given, let us assume that it is called the Tmax. It has been given that the maximum torque transmitted is 20% greater than the mean torque. So if we get 100% of the mean torque, we add there 20% of it, we shall get the maximum torque. And we have to also understand that Mean torque is actually that torque which is derived from the horsepower equation, which is given as power equaling to torque times omega, which is the angular velocity. Let us find what angular velocity is. We convert it to from actually n, which is revolutions per minute, to radians per second, and this is equal to 2 pi n divided by 60, and this is equivalent to 2 pi times 110 divided by 60, giving us 11.5 radians per second. What about mean torque? So from this particular equation, we can define mean torque as T mean, as given above, is equal to power divided by omega. Just by making it the subject of the formula, we have the value for power, we have the value for omega. When we substitute in 600 kilowatts divided by 11.5 to radians per second, it gives us 52,083.333 Newton meter. So when we proceed, we have assumed that the outer diameter is capital D and the internal diameter is small d. Now, if we are to continue, actually having assumed that, we know that Tmax is going to be useful. It's what we are going to use. So Tmax is equal to 20% greater than T mean, so that will be 1.2. That is just 100 plus 20% divided by 100. It will give us 1.2 times the mean torque. So when we substitute in the mean torque times 1.2, it gives us 62,500 Newton meter. Now when we go to, if we are to answer our question, we are going to consider two different design criterion, and here we are going to consider what we call the maximum shear stress condition, and we are going to see how it is applied. So from torsional theory, we already know that T out of J, T is the torque divided by J, which is the polar second moment of area, is equal to tau divided by the outer radius, is equal to modulus of elasticity times angle of twist divided by length. So when we consider T out of J is equal to tau out of R, this is what we get. The ratio of internal diameter to external diameter is already given, so we know that small d is actually equal to 3 out of 5 d, capital D, which is the outside diameter. But we also know these are knowns. Then R, which is the outer diameter, is also, outer radius, is also known as capital D divided by 2. So what about J? We know that J is equal to pi out of 32 into, for a hollow shaft, it will be the outer diameter to power 4 minus the internal diameter to power 4. So when you substitute in this equation here, when we substitute in that equation, we realize that this is J equal to R times T divided by tau. R, we have it as capital D divided by 2. We know tau, we know torque. So the torque we are using here is the maximum torque. Therefore, pi out of 2 into capital D to the power 4 minus D to the power 4 is equal to capital D divided by 2 times Tmax divided by tau. When we substitute in our values, we already know that the small d is 3 out of 5 capital D. So we substitute in and substituting the value for Tmax, which is here, and the value for tau. Then when we solve for D, when we simplify and solve for D, we realize that actually our outside diameter is equal to 182.7 millimeters. Now what about the small diameter or the internal diameter? It is given as internal diameter equaling to 3 out of 5, because that is the ratio that has been given. So 3 out of 5 times outside diameter, we multiply by 182.7, which is equal to 109.6 millimeters. So under steel torsional theory, we are going to consider angle of twist condition. Angle of twist condition, again we know from torsional theory, J is equal to TL out of G theta. So if it is equal to that, let us substitute in our values for J. We know J is pi out of 32 d to power 4 minus 3 out of 5 d to power 4. So when we put 3 out of 5 times d to power 4, then it will give us 0.1296 d to power 4. So you equate it to T, which is our torque, times length, which is 3, divided by G, which is 80,000 Newton per square millimeter. So to convert it to meters, to square meters, we are going to multiply it by 10 to the power 6. Then times theta, which is the angle of twist, and this will give us 0.01753. So when we substitute in our values and solve for D, we find that D is equal to 0.1988 meters and D is equal to 198.8 millimeters. It means 3 out of 5 times outside diameter. For considering the angle of twist condition, our internal diameter is going to be 3 out of 5 times 198.8, which gives us 11.9.3 millimeters. So when we compare the two values for internal diameter and the external diameter, we realize that this consideration gives us a bigger diameter, which is 198.8, greater than what we obtained above. And the internal diameter is 119.3 millimeter, which is greater than the one obtained above. Therefore, our shaft that we are going to machine or buy or to come out with must have a diameter of 198.8 millimeter and the internal diameter of 11.9.3 millimeters, so that it is able to withstand the stresses from both conditions. Thank you so much for watching.